Hello, and welcome to our discussion of the Wronskian determinant. This is material from the start of section 1.4.3. We'll begin with two differentiable functions, f1 and f2. They're only one times differentiable for now. And I'm going to define their Wronskian determinant to be the quantity w on f1, f2 at x is equal to the determinant of the following 2 by 2 matrix. The first column is f1 of x on f1 prime of x, and the second column is f2 of x on f2 prime of x. This is a 2 by 2 matrix, so its determinant is easy to compute. That determinant is f1 of x times f2 prime of x minus f2 of x times f1 prime of x. And the Wronskian will be a very useful tool for us now with second order equations and later on with boundary value problems. And we'll begin with lemma 1.4.10, which I'm going to call Abel's lemma. Suppose now that f1 and f2 aren't just differentiable, but they solve the following second order equation, f double prime plus a1 of x f prime plus a0 of x f equals 0. Allowing the coefficients to be variable here doesn't make life harder or easier. So if 1 and f2 solve this equation, and if I abbreviate w of x equals w on f1, f2 of x, then I know that w itself satisfies a different differential equation, namely w prime of x plus a1 of x, w of x equals 0. And this is just a computation that you're going to do through homework, your first homework assignment coming up. So we know or will accept that w of x satisfies a first-order linear homogeneous equation, w prime plus a1 on xw equals 0. And this tells us something important about w. Either w of x is 0 for all x, or w of x is non-zero for all x. So you have one of two possibilities. W is identically 0, or w is never 0. And why is that the case? Well, we can use the integrating factor method here. Indeed, the equation that w satisfies, w prime of x plus a1 of x, w of x equals 0, is first order linear homogeneous. It's an equation we saw deriving the integrating factor. And this equation forces w to have the form w of x is equal to a constant c times e to the capital A1 of x, where capital A1 is an antiderivative of little a1. That is, capital A1 prime of x is equal to little a1 of x. So w of x is constant times e to the capital A1 of x. We know a fundamental fact about exponentials. Exponentials by themselves are never 0. So w of x is non-zero for all x if the constant c is non-zero, or w of x is equal to 0 for all x if c equals 0. And there we go, that's the proof of our lemma. Next, we're going to study the much more involved theorem 1.4.11. Let's suppose that f1 and f2 continue to solve the second order equation f double prime plus a1 of x f prime plus a0 of x f equals 0. And now this is taking place on a particular interval contained in the reals. Then we have the following are equivalent, TFAE. This is our first, the following are equivalent theorem in the course, I believe. First, f1 and f2 are linearly independent functions on the interval I. Second, the Wronskian on f1, f2 is non-zero for all x and I. And 3, the Wronskian on f1 and f2 and x is non-zero for at least 1 in I. So you have 3 properties here, 3 useful properties related to the Wronskian and linear independence, and they are all equivalent. So if I know one of these 3 properties, I know the other 2 hold. That is, 1 implies 2, 2 implies 3, 3 implies 1, and also 2 implies 1, and 3 implies 2. So we are going to prove this step by step. First, we're going to prove 1 implies 2. We'll start out by assuming that f1 and f2 are linearly independent on I, and we want to show that the Wronskian on f1, f2 at x is non-zero for all x in I. We're going to prove this by contradiction. Suppose that the Wronskian on f1, f2 at x0 is equal to 0 for some x0 in I. What can go wrong with this? Well, If the Wronskian on F1, F2 at x0 is 0, then the determinant of this matrix, F1 of x0, F1 prime of x0, and then the other column, F2 of x0, F2 prime of x0, the determinant of this matrix is 0, so its columns are linearly dependent. And I have only two columns here. That means they're scalar multiples of each other. So I can find a complex number alpha such that the vector F1 of x0, F1 prime of x0 is equal to alpha times the vector F2 of x0, F2 prime of x0. This is just standard linear algebra, linear dependence, determinant being 0. Now here's the trick. I'm going to define a new function. H of x will be F1 of x minus alpha F2 of x. And what do I see about h? Well, just from my vector relation above, h of x0 is F1 of x0 minus alpha F2 of x0. So I just subtract the corresponding first entries in my vectors above, F1 of x0 minus alpha F2 of x0. That has to be 0. And likewise, if I take h prime of x0, that's F1 prime of x0 minus alpha F2 prime of x0, and that is also 0. So it looks like h at x0 and h prime of x0 are 0. These sound like nice initial conditions for an initial value problem. Recall also at the very start of our theorem, we assumed that f1 and f2 just weren't just any functions. They solve the same differential equation. F1 double prime plus a1 on x f1 prime plus a0 on x f1 equals 0. And so does f2 double prime plus a1 on x f2 prime plus a0 on x f2. This ODE that we started with is linear, like most of the ODEs in the course. And h equals f1 minus alpha f2 is a linear combination of f1 and f2. This just means h double prime plus a1 on x h prime plus a0 on x h equals 0. In other words, h solves the original ODE we started with. But in fact, h solves an initial value problem, a homogeneous initial value problem. H double prime plus a1 on x h prime plus a0 on x h equals 0, and then h of x0 equals 0, and h prime of x0 equals 0. Everything on the right side is 0. And you've read on your own from Lemma 1.4.7, one of the important facts we accepted without proof in this section, that this forces h of x to be equal to 0 for all x. But what is h? F1 minus alpha f2. So f1 of x is equal to alpha f2 of x for all x. This means f1 and f2 are linearly dependent, and this contradicts the linear independence of f1 and f2 that I assumed. So we have proved part 1 implies part 2. Now for something easy. We want to show part 2 implies part 3. We need to show that if the Wronskian on f1, f2 at x is non-zero for all x, then the Wronskian on f1, f2 at x is non-zero for at least one x. Well, this is immediately true. If something is non-zero for all x, then you can pick one x at which that thing is non-zero as well. So 2 implies 3. And now 3 implies 1, and we have to work a little harder. We are going to suppose that the Wronskian on f1, f2 at x0 is non-zero for one particular point x0 in my interval I. And I need to show that f1 and f2 are linearly independent on I. So what does that mean? I start out with the standard linear independence or dependence relationship. I have alpha and beta in the complex numbers, such that alpha times f1 of x plus beta times f2 of x is 0 for all x in I. And if f1 and f2 are to be linearly independent on I need to show that alpha equals beta equals 0. So I start out with my linear dependence relation star, and this identity is true for all x in my interval I, so it means I can differentiate both sides of it and get a new identity, double star, alpha f1 prime of x plus beta f2 prime of x is equal to 0. And now I'm going to plug in x equals x0 in both star and double star. And here's what I find. I find that alpha times f1 of x0 plus beta times f2 of x0 equals 0, and alpha times f1 prime of x0 plus beta times f2 prime of x0 equals 0. Remember, f1, f2, and x0 are given to me. Alpha and beta kind of arbitrary, so I can think of this system as a linear system in alpha and beta. In other words, I take my system for alpha and beta, and I'll rewrite it as a matrix vector problem, as I like to do. So this system for alpha and beta is equivalent to the matrix vector problem, matrix f1 of x0, f1 prime of x0 in the first column, f2 of x0, f2 prime of x0 in the second column, times the vector alpha beta is equal to the zero vector. And what is the determinant of this matrix? It's just f1 of x0, f2 prime of x0, minus f2 of x0, f1 prime of x0. That is the Wronskian on f1 and f2 at x0, and I assume that this Wronskian was non-zero. So my determinant is non-zero, the matrix is invertible, and I can uniquely solve for alpha equals beta equals 0. To recap, we have shown that if alpha f1 of x plus beta f2 of x equals 0 for all x and I, my 0 is missing here, sorry, that forces alpha equals beta equals 0. And what does that mean? f1 and f2 are linearly independent as desired, and I have shown that item 3 implies item 1. I have completed the full cycle of implications. All three are equivalent to each other.